Ni Maria Theodora, one of our IE faculty members.
Good morning. I'm Maria Chidora Gutierrez from the Industrial Engineering Program. Today I will discuss about multi-criteria decision making. So let's start. This webinar has four objectives. One, explain fundamental topics on decision making. Two, model decision problems by applying different MCDM methods. Three, provide students with methods to help them solve decision problems with multiple criteria. And four, improve students' decision-making skills. What is MCDM? It is a branch of a general type of OR models which deal with decision problems under the presence of several criteria. It is also termed as multi-attribute decision-making and multi-criteria decision analysis. Why do we need managerial decision-making? Because one of the responsibilities of being an engineer and being a manager is to make decisions. It is by process in which we respond to opportunities and threats by analyzing options and make decisions about goals and courses of action. There are several examples of MCDA problems, such as determine the best location for a new sports shop, given the following criteria: visibility, competition, and rental cost. Determine the best electric route for power transmission in a city, given several criteria such as cost, health, and reliability. Or determine the best candidate for a job given the criteria of work experience, interpersonal skills, and communication skills. So let's have a very simple example. Suppose I would buy a house and I come up with these two options, house 1 and house 2. I wrote the attributes of the house and indicated as a criteria. These are the lot size, number of bedrooms, number of bathrooms, location, and style. And these are their performance measures. So evaluating the two houses, we see that house 1 wins in the 3 criteria. It has the larger size, many bedrooms, and many bathrooms. In house 2, it wins in the two criteria, location and style. In location, it is proximity to work, so it is 10 kilometers. This is more nearer. We get the points. We just count it. 1, 2, 3 criteria wins. So 3 points here, 2. So house 1 is the best option for me. All right. Now, what if in my guts I like house 2 because it is a modern house? So what will I do in my decision process is to integrate my priorities on criteria. So in this case, we will just insert the weights. So I assign weights in 3 criteria as 1 and location and style as 2. These 2 points or 2 rating for the weights means this is my priority. This is twice important than the other criteria. So now we will aggregate the score of my options. House 1, the score times the weights, 1 times 1 plus 1 times 1 times 1 is 3 points. Here, 1 times 2 plus 1 times 2 is 4 points. So now we see that there is a change on the decisions. House 2 now becomes the best option for me. So integrating the priorities of your criteria will actually changes also your decisions. So that's the rational way of making a decision. So now I will move on to a more scientific method of decision analysis. we will discuss simple additive weights, and this is also known as weighted sum method. So, to evaluate the alternatives, we will come up with the overall score. And this is the formula. SI is equal to summation of their weight times the normalized value. So we have 4 steps in the simple additive weighting. We have determined the performance measures or scores of alternatives to each criterion. Number 2, normalize the scores of alternatives to each criterion by using the formula of RAG. 3, calculate the total score of each alternative using the formula for SIG. 4, select the best alternative. The one with the high score is the best alternative. So let's have an example problem. Suppose a company would like to build a new manufacturing plant and they come up with these 3 designs and they gave the 3 criteria. So we have parameters or performance scores of these designs to each of the criteria. And we see that this production capacity is the maximized objective. We want to maximize the capacity at the same time minimize the cost, operating cost and construction cost. What we will do is notice that these have different units. So this is in a million units, millions of pesos. So we cannot aggregate the score, get the total score. What we will do is to normalize the performance score. Here, we will divide the element by the best score here. So here for the production capacity, the best option for this is design 3. For the construction, the best design is design 1. And for the operating cost, it's design 1 and 2. So we write this one. And we see the formula a while ago in the simple additive weighting on normalization. So each element will be divided by the best score for the maximized objective. 7 divided by 9 is 0.79, 8 divided by 9 is 0.89, and 9 divided by 9 is 1. So for the minimization objective, we have divide the best score by the element, by each element. Here we have 6 divided by 6, 1, 6 divided by 7, 0.86, 6 divided by 8 is 0.75. So this goes with this the same. 3 divided by 3, 1, 3 divided by 3, 1. 3 divided by 4 is 0.75. Now you will see that the normalized value, which is 1, which has a number, score of 1, is the best score. So the higher the normalized value, that is the best score. Okay? So the third step for the simple additive is to get the weighted sum. In this case, the normalized value times the weight. So 0.78 times 0.3 plus 1 times 0.3 plus 1 times 0.4. So you got the total of 0.93. And then same goes to design 2. You will get the weighted sum. 0.89 times 0.3 plus 0.86 times 0.3 plus 1 times 0.4 equals 0.91. So this is with design 3. So the total score for each designs are 0.93, 0.91, 0.83, and the best design is design 1, the highest score. So that's the totality of simple additive weighting. Okay, it's very easy to follow. So I will just share the Excel file for this. I will give it later in the webinar. You can have this Excel file and the PowerPoint. Now here, in the Excel file, we have already discussed about the normalized value, how we come up with the normalized value, and the total scoring. Alright? So, design 1. Now, in the decision process, after knowing the best design, we will conduct sensitivity analysis because we want to know if the decision will be changed when the priority of criteria is also changed. So notice that we have 0.3 here and 0.4. What if I change my priority? I want to prioritize the capacity. So in this case, I will change the weight. So now I'll be conducting sensitivity analysis. So you have here 0.7, 0.2, and 0.1, which signifies that I prioritize the capacity over the other criteria. So what we will do now is to get the weighted sum. So our reference will be the normalized value multiplied by the weight. So we have 0.78 times 0.7 plus 1 times 0.2 plus 1 times 0.1 is equal to 0.84. So this is now the score of design 1. Next, it goes with design 2, 0.89 times 0.7 plus 0.86 times 0.2 plus 1 times 0.1 is 0.89. And the same with design 3. Now, you will notice that there is a change on the decision. Design 3 now is the best option for this, given that the weight of my capacity is high, or 0.7. So this is my priority, the capacity. Now, going further, we would like to know if prioritizing construction costs, what will happen to my decision. So here, we have 0.7 as my weights for the construction cost, and operating cost is 0.2 and just here 0.1. So again, we will get the total score by the normalized value multiplied by the weights. So this now is my new weights for my criteria. And to get it, 0.78 times 0.1 plus 1 times 0.7 plus 1 times 0.2 is 0.98. So the same with the other two designs. We've got 0.98, 0.89, and 0.78. So prioritizing construction costs will lead you to design 1 as your best options. Now, the last one will be what if I give a high weight for the operating cost, which signifies it is my priority, 0.7. So the same, we will have to get the total score. That's 0.78 normalized value multiplied by the weights, 0.78 times 0.2 plus 1 times 0.1 plus 1 times 0.7 is 0.96, and the same goes with the other. So we see that design 1 and 2 wins when you prioritize operating cost. So overall, we see the broader picture of our design, and we say that design 1 is more robust than the other design because design 1 wins in several algorithm. Alright, so as an engineer and designer, our aim is to develop or create a robust product or robust service that is not affected by the changes of the factors. It could be the criteria, priority, and so on. So that's it. That is our simple additive weighted method. That's the method 1 for the multi-criteria. Now moving on, I would like to provide you with another technique, method 2. So this one this one is termed as technique of order preference, similarity to the ideal solution, or TOPSIS method. So in this case, we will calculate the best alternative by determining which alternative has the shortest distance to the ideal solution and furthest distance from the anti-ideal solution. So let's have an example. The selection of the best product design. Here, suppose a company is interested in developing a new design for their product, and they come up with this for final design, and they gave the preferences of the criteria. And these are the functionality, profit per unit, environmental friendly, production quantity with their weights. The weight should be total 1.0. Now, we have the scoring or the performance score for each design. In functionality, it is a rating score 1 to 10, so it's a qualitative. Here, profit per unit, it's a quantitative measure. Here, it's a qualitative measure, and this one is the quantitative measure. So, in the MCDM problem, you can measure the alternative, you can measure the criteria on a qualitative scoring or in a quantitative measure. So here we have functionality. Of course, we want to maximize it. So the higher scored, the best it is, the desirable it is for the functionality. We have 7, 8, 9, 6. So design 3 is actually the best option with regards to the criteria functionality. Now, the profit per unit is also a maximized objective, environmental friendly, and production quantity. Now, we go to the first step in the TOPSIS. Now, we will have to know which of the design is the shortest distance to the ideal value and the farthest to the anti-ideal. So, step 1 is to normalize the performance score. This has different units, so we really cannot aggregate the score, total scoring. So what we do is that the formula for the TOPSIS is here in the normalization. RIA is equal to XIA over the square root of your summation of X squared IA. So in this case, the element is designated as your X. So here, the denominator, to get the denominator, you have to get the square root of this element. 7 squared plus 8 squared plus 9 squared plus 6 squared is 230, and get the square root. So after getting the square root, we will proceed with the remaining criteria. The same, we get the squared, the summation of the squared of the element, and get the square root. 9 squared plus 7 squared plus 6 squared plus 11 squared is 287, and get the square root of it is 16.941. The same goes to with the different, with the remaining criteria. Now, the table 1 for the normalized value, we have the element, each element divided by the square root of this value, this divided by this value. 7 divided by 15.165 is 0.46. 8 divided by 15.165 is 0.53. And 9 divided by 15.165 is 0.59. And here, 6 divided by 15.165 is 0.40. So this is the normalized value which we follow the formula in the TOPSIS. Now, this applies also the same with the remaining criteria. Now, after the making the performance score unitless, which is the normalized value, we will now get the weighted normalized value by the multiplying the normalized value to the weights of the criteria. So 0.46 times 0.10, 0.046, 0.53 times 0.1 is 0.053, 0.59 times 0.1 is 0.0459, and 0.40 times 0.1 is 0.040. So the same goes with the other remaining criteria. 0.53 times 0.4 is 0.213. So this is now the weighted normalized value for step 2. Now for step 3 of TOPSIS, you have to identify the ideal value and the anti-ideal. A plus is the ideal, A minus is the anti-ideal value. So to get the ideal value for the criteria functionality, we refer to the highest score in the table 2, the normalized value. The highest score for this is 0.059, so we write this as your ideal value. And for the anti-ideal value for this criteria functionality, we refer to the lowest value of this table, the weighted normalized value, 0.040. And the same goes with the other criteria. So that's step 3. Now, step 4 is to calculate the distances to the ideal value and the anti-ideal. So, step 4, distance, the formula is to get the difference of the element from the ideal value and then get and square the value. So you have here step 4, the distance calculation, 0.046 minus 0.059 and get the squared, and that's 0.0016. So that's the distance calculation. Okay, then another in the design 2, to get the distance calculation element, we have 0.053 minus 0.059 and get the squared. So the same goes to with the other criteria. Alright, so this one is step 4, distance calculation to ideal value. And another is to get the distance calculation to anti-ideal. So what you will do is similar with what we have algorithm for previous, except that the element will be get the difference of each element by the lowest score or the anti. In this case, 0.046 minus 0.04. Okay, so that's 0.046 minus 0.04 is, and then get the square, it's 0.0040. So this is the distance calculation to anti-ideal. Okay, so for this step 4, after computing for the distance calculation, we will get the summation of the distance for each alternative. Alright, so we get the summation, and in the summation, after you get the summation, you will have to get the square root. And that is now, we have the distance of the ideal value, which has a symbol of dA plus. So after the sum, you get the square root. Look at that, square root. Okay, and that's 0.0688. That is the distance to the ideal value. Okay, and then likewise in the anti-ideal, you get the summation of your distance calculation for the anti-ideal value for each alternatives. When you get the square root, you've got 0.083 and 0.034. Alright, and the last step for the TOPSIS is to calculate the relative closeness coefficient. You will get the ratio of your anti-ideal over your summation of ideal and ideal. So this is the formula for the last step in the TOPSIS. So you have the CA as your symbol for the coefficient. So CA is equal to dA minus over dA plus plus dA minus. So you will see here, given our step 5, dA minus, which is 0.083 over dA plus 0.068 plus dA minus 0.083 based on the formula, and you've got 0.552 as the coefficient closeness for design 1, and then we apply it to the remaining design, and we've got the highest score or highest coefficient, closeness coefficient, which is the design for. And this is our choice. The best choice for this manufacturing design is design for. Because we see that if the coefficient is closer to 1, that's the preferred alternative. So this is the highest for highest closeness coefficient. So we choose design for. So this is another method, TOPSIS, and I would also like to highlight some of the flexibility of TOPSIS. Like in step 3, it requires you to identify your ideal value and anti-ideal. Here, our reference, we rely on the highest score of your ideal value to the normalized weighted. Now, you can have some flexibility on this. You can have your own parameter. You can have your own value for this, and you will just follow the same algorithm as what I will be giving you here, the steps. All right, so that's it. I hope that you have learned something about the MCDM techniques and modeling. So thank you very much for listening.
Hello, Mike. And that is the multi-criteria decision making by Engineer Maria Teodora Gutierrez. If you were able to follow the discussion by Engineer Gutierrez, kindly key in MCDM on our comment section. Again, if you were able to follow the discussion of Engineer Gutierrez, kindly key in MCDM on our comment section. Ayan. Ang ibig sabihin MCDM, MCDM stands for Multi-Criteria Decision Making. Ayan. Their numbers.
Okay, good day everyone. So I'm about to present Pareto pairwise in the design project. So let's take a look at example number 1. So we have here design alternatives. So consider that we have 4 options, or we have 4 alternatives, design alternatives. Then that design alternatives are subjected to each performance criteria. Okay, so this would be the performance criteria, or the criteria number 1, criteria number 2, and 3. So we have cost of education, number of ABET accredited programs, and effectiveness of career support, in which 4 is the best and 1 is the worst. No? So let's say, for instance, we use pairwise comparison, okay, for this method. Let's say, for instance, comparing design alternatives 4 to 3. Okay. Then comparing 4 to 2, then comparing 4 to 1. Okay, so let's proceed with the first procedure, which is comparing 4 and 3. So as you can see, okay, this is actually highlighted. So we use a pairwise comparison for that. So cost of education, when it comes to the cost of education, the less is better. So when it comes to that design alternative, so offer 350,000. Okay, so for this performance criteria, option 4 won compared to option 3 because cost of education is lesser compared to option 3. Okay, when it comes to the number of ABET accredited programs, okay, the higher accredited programs, ABET accredited programs is better. So for this example, option 4 again, okay, is better compared to option 3. Okay, so when it comes to the effectiveness of career support, 4 is better. Okay, option 4 is better compared to option 3. Okay, so on this particular comparison, comparing design alternatives 4 and 3, okay, all performance criteria dominated by option 4, no, compared to 3. Okay, so it means to say in all criteria, the sign for 1. Okay, so again, so skipping that, okay, this would not be, this would be eliminated for our comparison since the sign alternatives for 1. Okay, so we compare 4 and 2 for the next procedure. So this one, 4 and 2. So when it comes to the cost of education, again, option 4, design alternative 4 is better. When it comes to the number of accredited programs, design alternatives 4 is better. And effectiveness of career support, design alternatives 4 is better. Okay, so again, okay, design alternatives 4 dominates design alternative 2. Okay, in all criterion. Okay, so the next procedure would be comparing option 4 and 1. Okay, the remaining alternatives. No. Okay, so in this design alternatives, option 4 is better when it comes to the cost of education. Again, for the number of accredited programs, option 4 is better again. Then effectiveness of career support, option 4 is better again. It means to say that option 4 in all design alternatives is better and 1 for different criterions. So after 3 pairwise comparison, okay, so we conclude that option 4 dominates all other options, design alternatives. And it is actually the best than the other options based on each of these 3 criteria. But in the design project, okay, well, it's Pareto, so it means to say, okay, it doesn't dominate all other alternatives. So that option 4 will not be considered, okay, in our design project. Okay, because there's no such design that dominates all criterions. Okay. Today for the example number 2, so we have 4 design alternatives, then the performance criterion would be the cost of cell phone camera image sharpness. 4 is the best, then 1 is the worst. Then ergonomics, 4 is the best, then 1 is for the worst. So consider that we have 4 design alternatives. This would be the cost of cell phone for each design alternatives. This would be the value for the camera image sharpness, which is 4 is the best, and ergonomics 4 is the best. Okay, so comparing options 4 to 3. Okay, so if we compare the options 4 to 3, when it comes to the cost of cell phone, okay, design 4 is better. When it comes to the camera image, design 3 is better. When it comes to ergonomics, design 4 is better. So neither one dominates the other for this comparison. Okay, so for comparing 4 and 2, option 4 and 2. Okay, so for option 4 and 2, okay, so when it comes to the cost of cell phone, option 4 is better. When it comes to the camera image, option 2 is better. When it comes to ergonomics, option 4 is better. So the comparison of option 4 and 2, okay, neither one dominates the other. Okay, how about comparing option 4 to option 1? Okay, for the cost of cell phone, 4 is better. When it comes to the camera image, design 1 is better. When it comes to ergonomics, okay, option 4 is better. So comparing option 4 and 1, neither dominates the other. Okay, so comparing about, again, 3 to 2. Okay, so cost of cell phone, option 3 is better when it comes to camera image. Option 3 is better again. When it comes to ergonomics, option 3 is better again. For this, the sign alternatives to, okay, this would be eliminated, no, for our Pareto optimal. Okay, because all of the criteria mentioned was actually dominated by option 3. Okay, comparing 3 to 2. How about comparing option 3 to 1? Okay, so when it comes to the cost of cell point, okay, option 3 is better. When it comes to the camera image, option 3 is better. The ergonomics, option 3 is better. So again, option 3 dominates option 1 in all the criteria performance mentioned. So this would be eliminated. This would not be considered as a Pareto optimal. So the remaining would be, we are left with options 3 and 4. If we are trying to compare it again, okay, this one for the cost of cell phone, okay, alternative 4 is better. When it comes to the camera image, alternative 3 is better. When it comes to ergonomics, okay, option 4 is better. So this would be considered as a Pareto optimal, the options 3 and 4. Okay? Okay, for example, number 3, we have again, if we consider for alternatives, then the whatever the performance criterion is, okay. So comparing 4 to 3, okay, again, let's do the pairwise comparison. 4 to 3, so 4 is better, okay, the option 4 is better. Okay, when it comes to the performance criteria 2, option 3 is better. When it comes to performance criteria 3, option 4 is better. So neither dominates the other. Okay, again, comparing 4 and 2. Okay, performance criteria 1, 4 is better. When it comes to performance criteria 2, okay, the sign 2 is better. Performance criteria 3, the sign 4 is better. So neither dominates the other. So comparing option 4 and 1, okay, 1 is option 4 is better. Then option 4 is better in performance criterion 2, and option 1 is better in performance criterion 3. So it means to say comparing 4 to 1, okay, when it comes, comparing option 4, okay, here to 1, okay, in all criteria, okay, 1 is highest, okay, compared to 0.8, then option 4 is better. When it comes to performance criterion 2, option 4 is better because option 1 is 0. When it comes to the performance criterion 3, option 4 is better. So the sign 1 was actually dominated by option 4. So option 4 dominates option 1. So this would be eliminated and would not be considered as a Pareto set. Okay? So how about comparing option 3 and 2? Okay, comparing option 3 and 2 performance criterion 1, option 3 is better. Performance criterion 2, option 3 is better. Performance criterion 3, option 2 is better. So neither dominates the other. Okay, so no need to compare 3 to 1 because 1 is already eliminated. Okay, so the remaining would be option 2, okay, 2, 3, and 4 are said to be Pareto optimal or Pareto set. Okay, how about for example number 4? So we have If we compare each of these design alternatives 4 and 3, okay, when it comes to each criterion, okay, it would result that any of the design alternatives neither dominates the other. Okay, it means to say there's no uh, design alternatives that dominates other design alternatives. Okay, it neither one dominates the other. Okay, so this would be considered as a Pareto set, all of the design options. Okay, when it comes to the linearization, okay, so we have a formula here, okay, because in our design, there are different measurement we used to identify each criterion. Let's say, for instance, for design, for the example number 1, we have here cost of educations, it's pesos. This one is units, and others are for in the scale of 4 to 1. Okay, 4 is the best and 1 is the worst. Then to linearize it, okay, to have a common number for each of the criteria, which would be considered later on. Okay, so we have here to convert that into numbers. Okay, okay, 1 to 10, as 10 being the highest. No? So we use this linearization. Okay, so we have, if the first equation is this, okay, if our first performance criteria, we normalize that, this would be the equation for when the best is smaller value. Let's say, for instance, the best the smaller value for cost of education. When it comes to the cost of education, the smaller value is the best. So we will be using this equation. Okay. When we use this, when the higher value is better, so we use this equation. Let's say, for instance, the number of accredited programs. The higher, the better. So this would be the equations for that. Okay, let's say let's have an example. Okay, which is, for example, number 1. Given an example number 1, of course, 4 is not included anymore because it dominates all the other options. It means to say that in all performance criteria mentioned, okay, option for 1, okay, so this would be included, not included anymore. So the alternative design 3, 2, and 1 would be considered as Pareto set. So that would be considered for our linearization. Okay. So as we go on to our linearization, okay, for the cost of educations, the equations used is that when the best is a smaller value, so we use this equation. So you can see it's already tabulated in Excel. Okay, so 9. Okay, the maximum in the row. Okay, here. Okay, in that row, this means to stay. Okay, then minus the performance criteria for that row, which is this one. Okay, this is the performance criteria for that row that we're trying to get the values for linearization. Okay, then over, okay, the equation is max. Again, we use that to highlight this one. Okay, for D107 to 109. Okay, just follow the formula. Okay, then minus the minimum in the row will be selected by the Excel. Okay, 100 for the cell 107 to 109. Then plus 1. Okay, so this would be the result. Okay. Okay, then just need to copy that. Okay, in the Excel, Control C, then Control V for the next, no? And Control C and Control V for the next. Okay, so for the number of accredited programs, for the equations used for that is this one. Okay, when the best is higher value. Okay, again, the use of these equations are uh, through Excel functions. I just need follow the formula. Okay. And so on and so forth. Okay, so that's it for linearization. So the linearized value for our example number 1 is that this one. So we consider here, okay, for option 1, 2, and 3, this is the linearized value. Okay, so looking at the options now, who got the 10 scale, okay, this is better, and this is better. Okay, for our example number 2, okay, for, again, cost of cell phone, we'll use the equations, this one, when the smaller value is the least cost. Okay, the camera image, okay, the higher value is the best, this one. Again, for the ergonomics, is this one. Okay. The same with example number 3, and so on and so forth. Okay. How about for those criterions that we should need to give weights? Okay. Remember that we have, let's say for example number 1, this is our performance criteria, and this one would be the level of importance or the criterion's importance, which is we rank it 1 to 10 or 0 to 10 rather. Okay, then we have the weights would be automatically computed based on the level of criterion you set. Okay, then your design options, design 1, design 2, and design 3. Okay, so let's say for instance, okay, for the ergonomics, okay, on the perspective of the client, okay, they would consider that uh, in their the importance of this criterion, they set it 10, and the number of ABET accredited programs, they set it 10. Then the effectiveness of career support, they set it 10. Okay, so all in all, it's a 30. Then of course, the weights would be automatically be given based on this the average of this. Okay, just need to divide the that criterion to each, to the summations of that. Okay, so you can get automatically the weights. Okay, so let's means to say for the design one, okay, you will be applying 33%. Okay, for that weights. Okay. And 33% for the results for design 2, and the result for design 3 is also, you multiplied it with 33%. Then the results would be like this in percentage. Okay. And this one. And after getting the percentage, you can actually compute the for each design, okay, the percentage of each design per criterion. You add it up, okay, this would be the percentage per design. Okay, example, if you have, okay, let's say for instance, if you have performance criteria, or decision criteria rather, you have economic, safety and health, and environmental. Okay, then the level of importance or criterion importance range to 0 to 10. Okay, this is actually answerable by the client. Okay, so 10, okay, then 9 and 8. So it would be automatically it would give weights automatically based on the level of criterion set by the client. Okay, or the perspective of the client. Okay, then we have three design options. Okay, let's say for instance this is the linearized value already. Then if this is the linearized value already, we get it from, okay, from the conversions to the raw values to the linearized value. Okay, then how we are going to apply these weights? Now you just need to multiply it. So you have 37% and so on and so forth. Then for this design one, okay, let's say for instance 100%. For this design two, this would be considered 96% total. Then for the design three, 67% total.
And so if may questions kayo, ayan, feel free to open your microphones lang or yeah, type it sa ating comment section and our speakers will gladly answer those questions accordingly. Especially kapag may kinalaman talaga yan sa MCDM at Pareto optimization. Ayan, bilang yun yung gagamitin ninyo sa inyong design projects. It's a good thing na ngayon pa lang tanongin na natin if we have mga hindi naiintindihan na portions para ma-clear tayo kasi baka others din ganun din yung yung hindi naiintindihan or medyo gray area. Ayan. Parang meron nagsalita, meron ba? Meron? Pakigalaw ng basa. Wow. Ayan. So again, if you happen to have questions, you may write it in our comment section or you may turn on your microphones. And thank you very much for those who commented, ayan, Pareto. It goes to show that you were able to understand and follow our discussion. And it goes to show that you were able to hear my voice clearly, ayan. Hindi na, walang putol-putol. Ayan, sige. So let's have our countdown kapag wala tayong questions in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Sige. Ibig sabihin walang questions, no? Tama ba? Sige, let's move forward and that concludes our question answer portion. If you happen to still have questions with you regarding the topic discussed today, halimbawa may mga naisip kayo nagpop-up na question after this session, feel free to send an email to tipqc.i@gmail.com. The email address will be posted on the screen. Ayan. Kung may questions kayo na sa tingin nyo nag-pop up sa inyo after this session, feel free to message it there. Tapos our speakers will still answer those questions. I-replyan natin kayo dyan. Again, it's tipqc.i@gmail.com. Now, at this juncture, we request everyone to turn their cameras on and wear their best smiles for we will be having our photo opportunity. Ayan. Ano tayo? Retouch. Open tayo ng microphone for we will be having our photo opportunity. May I also request the screen sharing to be stopped. Stop. Para kita natin